Okay, guys, good evening.
Hello, teacher.
Hello, guys. Okay, we have more people joining in. Let's just give it a few more seconds. Let's just give it a few more seconds. And we have 24 people, which I think is roughly the same amount of people we had last lecture, like roughly. I mean, let's see if more people join in. Did people drop out of the class, or are we just not coming to lectures anymore?
I guess it's the second case.
Okay. Well, we'll see how that goes. Okay, let's get started. Let me open the slides for presentation today. And let's see what happens. Okay, so can you guys see the slides?
Yes, teacher.
Yeah.
Okay, awesome. So last time we were talking about ultrasound transducers. We talked about the near field. We talked about the far field of a transducer, right? And I think we actually made it all the way to focus sources, and we finished or wrapped it up right before talking about ultrasonic arrays, correct?
Yeah, we stop here.
Fantastic. Well, then let's talk about the wonderful world of ultrasonic arrays. Ultrasonic arrays are very important for us in medical imaging, because those are, to a very, very large extent, this is, 99.99% of the types of arrays that you're going to see in practice. Okay. Single element transducers, you probably get to see them in non-destructive evaluations and in very, very specific cases of, medical, I don't know if to call them imaging. It would be more like tissue characterization. There are some commercial devices that use single element transducers. Most of them will use arrays. And the reason for that hopefully will be very evident, by the time that we finish this discussion. An array, like the name would imply, consists of a collection of sources, right? Which I'm marking in red in here, so on and so forth. And in this particular case, these sources are arranged in a line at a uniform spacing in between the elements. There are many things that one can say about this. That is not to say that all the arrays or the transducers that we use in clinical practice have this configuration. We'll talk about other configurations also during these lectures, but even outside of the scope of the lectures, you can go to the literature and read about things like sparse arrays, for example. Like if you ever have the time and the willingness to do it. Sparse arrays are arrays that do not have the elements, uniformly spaced in whatever arrangement, right? I mean, the spacing in between the elements is actually non-uniform, and that provides some benefits, and actually has some drawbacks when doing ultrasonic imaging. And the reason for that, we can actually get to talk about that later. You can read about, for example, 2D arrays, which we are not going to cover either in the context of this course. So again, they don't have to be arranged in a line or in a curved line. They can even be arranged in a 2D grid. And with those arrays, you could directly perform three-dimensional imaging, for example. But remember that we are going to first order principles in most of the things that we are doing in here, right? So we are going to explicitly discuss just this case, which is several elements, right? In this case, it will be 1, 2, 3, 4, 5, 6, 7 elements arranged in a line. The spacing in between the elements, the separation in between adjacent elements, is given by a fixed value d, little d, whatever the value is. Overall, we would have, a total length of the array, which is going to be equal to n minus 1 multiplied by d, where n is the number of elements we have in the array. The array in this particular configuration is laid out along the y-axis, and it's going to irradiate in the xy plane, right? The perpendicular plane, of course, will be the z-plane. And in this case, because the sources are point sources, there would be a complete omnidirectional, right, pattern in the elevational direction, but we have directivity, or we're going to see that we're going to have some directivity along the xy plane. Okay.
Teacher, will it be like some sort of cone around the x-axis?
It would be like some sort of a cone. If we so if we get to think about it, it would be something that it has to look the same, right? No matter what you do. Like in the elevational direction, because you have no directivity there. In the x and y, you actually will have, some sort of a beam, right? And that's just what it is. So it would actually be more like a, well, I guess depends on how you want to conceptualize this, right? But I suppose it would be more like a donut shaped. Like if we were to focus it, I suppose, like or a ring, right? Because you would achieve some sort of a beam, right? That has like some shape. Imagine that eventually we focus it, and we'll talk about that too, right? But let's say the energy is concentrated in some location, and that would be, relative to this angle over here, which is the theta angle within the inside the imaging plane. But away from it, right, it would exactly be the same thing, right? So that's roughly what it would look like. It would just, create a rotational symmetric body across the z-axis, I suppose.
So it will look the same as the focusing region we've seen before.
Right. I mean, in principle, like if you really think about it, correct? If we're doing something like this, what we're displaying here, the sources are just going to irradiate in general, right? I mean, they're going to operate in some fashion. And because the sources are arranged in the x and y plane, then something will happen in the x and y plane, correct? But we can actually very easily envision this, from the fact that because there is no directivity whatsoever in the z direction, right? Everything is just radiating freely in the z direction. Then it actually gets to be inconsequential, exactly, like where you are on that z. But it matters where you are in the x and y plane, right? So there it actually does matter. Or said in a different way, it's basically, right, it becomes something that basically depends on where you are located to this axis over here, right, given by the distance r. Because I mean, at any point that shares the same distance, then it would have to be equivalent, right? And again, you can think about it, or you can hopefully conceptualize it based on the discussion that we were having on the previous lecture where we talked about the directivity patterns eventually being related to the Fourier transform of the apertures, right? So you can roughly identify what the pattern should be, right? The diffraction pattern eventually should be. The tricky one probably to conceptualize would be what's the pattern that we should be observing, right? If we were to analyze this in the X and Y plane, right? Because it actually involves, you know, calculating the Fourier transform of an arrangement of points, right? And you have an arrangement of points along a line. You can actually do the calculations. It's not really that difficult. The way to set this up would be to argue that what you have is a pressure field, which is going to be, you know, the summation of, you know, a e to the minus jk capital R sub I divided by R sub I for I going from, let's say, 0 to n minus 1, right? And hopefully you guys recognize what this is actually saying, right? It's saying that every point source in the array is going to be fired at the same time, right? Because they all apparently are fired at the same time. And the overall pressure field is going to be the contribution of capital N point sources, right? Each one of them has a distance from the point source to the observation point. That would be this R sub I variable in here. And like in principle, it's very easy to calculate, especially if you were to do this with a computer, for example, right? So it's, again, it's relatively straightforward to do. Not completely trivial though, but it's relatively straightforward. If you were to actually do this or to calculate this using the far field, this of course would be the far field expression or approximation. In this case, I guess it would be more accurate. So let's say, let's delete this. So an expression is an approximation. What you would have would be this equation over here. The pressure as a function of R and the angle theta, which is the angle that it would make relative to the, right, relative to the x-axis in the xy plane, would be given by n, which is the number of sources, times a, which is the strength at which each one of the sources is radiating, times e to the minus jk r divided by r, which is just the radiation of a point source. And then multiply by this horrible thing here, which we know that it would have to be the Fourier transform of, you know, a group of delta functions distributed uniformly across a line, right? That we know. We probably didn't know that this was a solution, which is kind of different, right? But that's what it is. And this function, if you get to see it, you remember the sinc function, right? And the sinc function is something like sine of x divided by x. And, you know, there are people that would define it differently. And some people would say that it's sine of pi x divided by x or sine of pi x divided by pi x. But in the end, it's kind of the same thing, right? So this function over here is a sine divided by a different sine, right? It's actually a different sine function that is, if you pay attention to the arguments, right? The only difference is that the sine, the argument of the sine function in the numerator is capital N times the one in the numerator.
Yeah.
If, for example, 1/2k times little d times sine theta, right? All of that would be a very small number. We know that that sign in the denominator would converge or would become approximately equal to the argument And if you pay attention to that, the numerator and the denominator, right, under that approximation, the denominator would be the argument of the sign in the numerator, right? Again, if you assume that the whole argument of the denominator of the sign in the denominator is small, then the sign becomes the argument. And then you have this capital N over here. So you will have sine of 1 over 2 n k d sine theta divided by 1 over 2 n k d sine theta. And that would be a sinc function. That's the reason why this function gets the name of a sampled sinc. And when you really think about it, it's not that illogical, okay, that it would be something that relates to a sinc function, because I was saying, right, if the argument in the denominator of the sign in the denominator gets to be very, very small, what would that mean? That would, for example, mean that the separation in between the point sources in the array is very small, right? So if you conceptualize it, that would be like you have a whole bunch of points that are infinitesimally close to one another, right? D goes to 0. If I have something like that, then what would my transducer be?
A line.
Correct. It would stop being a collection of points. It would become a solid line, right? And if it is a solid line, then the directivity would have to be the Fourier transform of that line, which is a rectangle function, right? Because it's 0, then it's something, then it's 0 again, and that would be a sine function. And probably if you visualize this transducer like being a line, right? Hopefully you can better visualize that there has to be symmetry, right? In the directivity pattern, because it's just a line that's radiating everywhere, right? So you would expect that in the direction, like in this direction, right, there would be complete and total symmetry. So hopefully that also helps clarifying the questions in the previous slide. Questions up to this point? Awesome. Now, we can also, and by the way, I'm assuming that you already read all the slides, right? So I'm trying to basically, you know, just go quickly through the contents of the slides. And the idea would be that if you have questions, then you have to raise your hands and ask away, okay? Because you had the slides there for, you know, a couple of lectures already. So I'm pretty sure you all read them, you know, from start to finish like 20 times. So now the thing is, when we plot the directivity function of the sampled sinc function, right, that we saw earlier, we can do that. For example, in this case, you have arrays of 10 elements. The separation is equal to have a wavelength on the left and 2 wavelengths on the right. Okay, and what you get to see is that the plot on the left, I mean, kind of looks like a sinc function, right? I mean, there's a main lobe, and the main lobe points at 0 degrees, which is what you would expect, right? I mean, it's the ultrasound is propagated going in the front because it has that symmetry, right? I mean, you would expect that the beam would be, you know, like perpendicular to the direction of the line. And then you have side lobes, right, which are in here, like in here and in here and in here and in here, and they get to go like increasingly lower amplitudes, and everything is fine. What happens when you have a separation of, let's say, 2 wavelengths in between adjacent elements? What do you guys observe in the plot on the right? I mean, you will observe a couple of things, right? The first one is that the main lobe gets to be narrower. Why would that happen?
Because of the same reason, the scaling property for the transform.
Because the number of elements remain the same, right? Yeah. Because the spacing increased, the overall length of the array increased. And because you have a bigger array, then if you actually look at the directivity, as a function of the radiation angle, then you have a narrower main lobe, right? But what else do you observe?
A big main lobe that appears like nearly the 90 degrees, which I think would be the borders of the line.
Like this, and you also see this, right?
Yeah.
What you see over there, right? The things that you observe over there are what are called grating lobes. Grating lobes are a very, very sad side effect of violating Nyquist criteria. In other ways, side lobes appear because of aliasing, basically. You guys do know what aliasing is, correct?
Yeah.
What's aliasing?
It happens when you have an discrete harmonic wave and you want to describe it, but you get out of the fundamental range, then what you may describe inside of the, I don't know, maybe pi/3 outside the fundamental range gets repeated.
Sure. Does somebody want to provide a more formal definition of when does aliasing occur?
It occurs when you have a sampling frequency and two different signals can become like indistinguishable between one another because of your sampling frequencies.
What's the condition with the sampling frequency? Whenever
it
you
has
have
to be
aliasing,
2 times the minimum sampling frequency.
The maximum frequency of the signal.
If the sampling frequency is lower than the Nyquist, right?
Yeah.
So basically, if you have a signal that has an overall, like it goes in frequency as high as, F maximum, then your sampling frequency has to be at least the Nyquist one, which would be 2 times the F maximum, right? Roughly, that's what it is.
Yeah.
Meaning you need to sample, and I guess overall, everything that you guys were saying, it's basically what it is, right? I mean, you need to have, at least 2 points per period in order to properly describe a sinusoidal, right? And the classical example of when aliasing happens, right, is when you have a very high frequency sinusoidal and you start grabbing samples very far apart, right? Like, for example, you have something like this, and you have one sample here, one sample here, one sample here, one sample, and so on and so forth, right? Or something like that. Hopefully I did this right. I'm thinking I didn't, but you get the point. So if I start to get samples very far away from each other, rather than, there's a whole oscillation in here, but I'm seeing this as it is a constant, right? Because I'm sampling this, one period away from each other, the points. So what I see, instead of a high frequency, I see a flat thing. Something that was supposed to be very high frequency, I observe it as low frequency, right? So whenever I'm sampling something, but I sample that something below a minimum sampling rate, I'm going to start losing information. And that information that I'm missing out is going to do what? Is going to distort the information content of that signal, right? Which, again, makes total sense. I'm not properly sampling the signal. I'm wasting information. Something bad has to happen. In the context of the Fourier transforms, then yeah, the aliasing just means that, right? You were supposed to be measuring something that had a frequency in some value, but because you're not respecting Nyquist, you're observing the actual frequency in a different location. which ends up being, you know, a lower frequency than it was supposed to be. The same thing is happening here, really, when you think about it. Because if you want to conceptualize what an array is, it is a way to construct a transducer that would actually be a line. Right? I mean, it was supposed to be a line, but I don't want to manufacture a line. So what I do is I create my line by placing a whole bunch of points. This was actually something that was done by people in the radar community, for example. Right? I mean, in radars, you want to, for example, if you want to look away from, you know, planet Earth, you want to look at things that happen, you know, outside the atmosphere. People wanted to have very big, you know, apertures, but those were super difficult to put together. You know, if you want to have an antenna that's like kilometers in size, that's a challenge, you know, from a mechanical design point of view. Because the material has weight, you know, it would fold, it would, you know, collapse, the shape of the antenna would distort. So what people found out was that they could actually, rather than, you know, building a ginormous antenna, they could actually place, you know, a whole bunch of small antennas distributed over an equivalent surface and synthesize the antenna that way. Actually, people were really clever, you know, and there are some things like synthetic aperture, which means that you don't even have to have a whole bunch of antennas. What people did was they had one antenna, you know, and they kept moving the antenna. Right? So instead of having, you know, antennas spanning, I don't know, 10 kilometers, you have one antenna and you move it in a truck, you move it in a train, you move it on a plane, you know, so you can actually create images that way too. So in general, people have tried to do, you know, a whole bunch of very, very clever things. And that's the same idea in here. What you're trying to do basically is you're putting together something that looks like the solid line. It's just that, you know, you're constructing it with a whole bunch of, you know, tiny elements rather than having one solid line. But what you're doing is you're sampling that line. And if you start to sample that line very coarsely, that is with the elements too far away from each other, with the samples too far away from each other, then you have to pay a price. And the price that you pay is that you will distort the frequency spectrum of the signal that you're producing. And that's the reason why you get this, you know, these grating lobes that are just an effect of aliasing. The content is spreading out all over the place because you have your samples too far away from each other. Having them too far away from each other is the equivalent of you're not sampling fast enough. You're not respecting Nyquist. And we're going to see this, you know, sampling problems and aliasing effects at least one more time in the context of ultrasound when we study Doppler imaging, just so you know. So the grating lobes are going to occur in angles at which the denominator of the equation that we had before for the radiation pattern will vanish. And you can actually, you know, go to that equation and simply, you know, look at the argument, and you can find out that that will happen in locations where the sine of the angle is a multiple of lambda divided by d. Lambda the wavelength, d the element separation. So there you can actually see that, you know, in the event that d is actually smaller than a wavelength in general, right? If d is lower or equal to the wavelength, smaller or equal to, then lambda divided by d is going to be a number that is, you know, equal to or larger than 1. Because m is an integer, right? Then you're going to have grating lobes at places where the sine of theta is going to be, you know, equal to or larger than 1. And that in principle doesn't have a solution, right? Like technically speaking, if you make lambda and d be equal to each other, then yes, you will have one grating lobe at 90 degrees. Okay, that's the reason why, in order to not have a grating lobe whatsoever, what people did was they came up with this rule over here where d divided by lambda was going to be less or equal to n minus 1 divided by n, rather than less or equal than 1, which is something that you would probably guess, you know, from this equation over here. That expression down there comes from actually making it such that rather than having, you know, the location of the peak here, right? So it would, you know, at 90 degrees, you will have the grating lobe. What you actually make it is that the last zero before the grating lobe lands at 90 degrees. If you, which you can actually do, because, you know at which locations that's going to happen. Those are the locations at which the numerator goes to 0, but the denominator doesn't go to 0, right? So that's the way, and that's the reason why that n minus 1 divided by n appears in the equation, because people actually, what they do to come up with that expression, they go for, you know, the solution which gives you the maximal spacing such that the last 0 before, you know, the 0 that corresponds to a 0 of the denominator happens at 90 degrees. That's so just so you know where that equation comes from, okay? But in general, if you really think about it, you can take it for granted, because when n is relatively large, you know, 50 elements, 100 elements or whatnot, then really what that expression is saying is if d is less than a wavelength, right, with some small margin, then you're not going to have grating lobes. Pirol has you have your hand raised. You want to ask a question?
Yes, sure. I just want to know if I understand about
Sure.
the pattern that is formed with these dots of the transducer. When we have this kind of aliasing in the case of having a d greater than a lambda, it's like we're having like more than one focus point at the same time.
It's not focusing per se, right? I mean, it's like focusing, we reserve it to the actual case where, you know, to the actual case where we are curving the shape of the transducer such that every element in the transducer aperture is at the same distance away from a point, right? In this case, what we're looking at is the radiation pattern in the far field. And yes, I agree. We still have a main lobe, right? We have a beam. We have an ultrasonic beam. It's just that it's probably very, very wide, right? Because we're in the far field and God knows. And we kind of know that, you know, that size of the beam is probably comparable to the extent of the array anyway. Focusing again, we reserve it to the case where, you know, for example, for a circular piston, we actually curved the circular piston so that every point was at the same distance away from every point in the surface of the piston. Just some clarification, right? But technically speaking, yes, what you're saying overall is correct. What this implies is that, you know, for example, if I were to have an array and I have aliasing, right? And let's say that this is my array with aliasing. And let's say that I place in here, right, an object, and I have, let's suppose that I have a region that was supposed to be anechoic, right? Let's suppose that inside that circle, there were supposed to be no ultrasound reflectors whatsoever. So I should observe that circle pitch black. Okay, what happens is that when I turn my transducer on, there would be the main lobe in here, right? But there is also, let's say, a grating lobe in here. And actually, well, I mean, very likely I will have the grating lobe in here too, right? Because it's symmetric anyway. So what you observe is that, you know, in principle, I should be, when I receive echoes from here, I should receive nothing, right? Because there are no reflectors. The main beam of the transducer is pointing in that direction, and there is no reflection coming back. But, oops, right? I mean, what happens is that I'm also getting signal from here and from here, right? And in those two regions, there are reflectors. So
Okay.
in the end, what's happening is that, you know, information from here and here is going to be fold back into here, because my imaging apparatus would have no mechanism to discriminate between those two. It's just receiving echoes. And it's, you know, crossing fingers that we did a good job at designing the system such that the echoes are coming from front. But if we did a poor job and we're getting signal coming from the sides, there's no way to discriminate those. Not
Yeah,
like this, at least.
in that case, that would be a biased like measurement, because that range that you are measuring is not anechoic as the inclusion that you want to measure. That
Correct. So
Okay.
you will have a bias in the echogenicity. And that can have, you know, a profound effect, of course, like let's say for breast cancer imaging using ultrasound, if you have a lesion that is anechoic, then that's very likely a benign lesion, right? That could be an anechoic, like a fluid filled cyst, for example. And that, you know, clinicians would be like, oh, this is nothing, you know, but it could be hypoechoic, meaning that, you know, it has a shade of gray, it's not completely black, and it's not as echo generating as, you know, the rest of the breast parenchyma. And that could potentially be a concern, you know, for maybe this being cancer. Not really like that, because people would not only look at the level of gray, right? But you kind of get the point. And yeah, I mean, that could actually have a profound impact on that, right? Because it may be that it's just because you're having grading lobes and you're measuring things that you're not supposed to be measuring anyway.
Okay,
So it
thanks,
could matter.
Lucio.
Sure, no problem. I think there is something in the chat. Is it like a superposition of information that we don't want? Correct. That's exactly what it is. Again, what this is saying, what these plots are showing us, is that the transducer is radiating, right? That it not only has one beam, but, you know, like out of whatever it has, you know, like in this case, it will have 5 beams, right? I mean, one pointing at like sort of like 30 degrees and another one at close to 90, and then at minus 30, and then at minus 90, and then at 0 degrees, right? I mean, very likely, you know, the side lobes at 90, they're not going to matter anyway, because they're like, you know, broadside of the transducer, so that really doesn't matter. But the ones that, you know, are pointing in, let's say 0, and the ones at 30 degrees, those are going to matter, very likely, right? And that again is a challenge, right? And this is something that people very early recognized when designing ultrasound transducers, and actually back from the radar community days. And it's again another reason why it becomes very, very important to have these tools that would analytically allow us to predict what the radiation patterns would be, right? Because I mean, you can catch on things like this, which are, of course, you would imagine super important that you're aware of. More questions? Awesome. There is a reason why, and there are many reasons probably why we are studying an arrangement of point sources rather than, I mean, I said that I'm using a group of point sources rather than having a solid line, right? And it's probably a very bad argument, right? I mean, probably for the people in the radar community, again, that makes sense. Because, you know, I mean, the things that they will have to put together again were kilometers in size, right? But in our case, I mean, we're talking about like what, like 4 or 5 centimeters length thingies. I mean, that we can surely put together, you know, some radiator of, you know, 5 centimeters in size or 4 centimeters in size. That's not a problem. There is another reason why we do this. The reason why we are using different elements to synthesize or to simulate that we have a bigger transducer is because we can individually excite every element. And that will allow us to do things that we wouldn't be able to do if we were to have a solid radiator, a one-piece radiator, okay? Again, I know that you have probably gone over the material right now, so I can, try to skip on a few things, and also hopefully you know the kind of things that we can do. One of the things that we can do is we can rotate the axis of the transducer. And the math to do it is extremely simple, actually. It's shown in this slide over here, which is basically telling us that if you apply time delays to each one of the elements, and these time delays follow a linear sequence, right? So for, let's say, the element 0, you apply it, with a tau 0, then or something like a t of tau, and then for the element 1, there's 2 tau, and then for 2, it's at 3 tau, and so on and so forth, right? So you keep, like, the delays that you apply to each of the elements keeps increasing linearly as a function of the position of the element. If you do that, with some time constant tau, then you would be rotating the axis of the transducer in a certain amount of degrees that satisfies that sine of theta naught is equal to c, the sound speed, times tau, the rate at which you are increasing the delays, divided by d, the separation in between adjacent elements. C times tau, right, becomes a distance of sorts, right? It's actually the distance that the ultrasound would travel, like in between the firings of two consecutive elements. Because you fire each consecutive element with a delay of tau, so the distance that that wave travels is C times tau. And then you divide it by the actual separation in between the elements, right? And that gives you the angle that you're going after. You can actually even think about it, from geometrical considerations, probably, right? Because again, you have some lateral distance of d, and you have some axial distance, right? That the ultrasound would travel in between the firings, that will be C times tau, right? And that's basically what it's saying, is that ultrasound would, flip in that angle, theta naught. Basically. So again, that you can actually, derive it even from first order considerations. If you were to go through the math, right? Starting from the original equation of what the pressure field should be, and then doing all the math, combining all the things together down to the point of where we are, right? Now, you would get to this second equation that's in here, which is slightly more complicated, but again, that's basically what it's telling you, is that the axis rotated in theta naught degrees. In order to avoid the grating lobes, it becomes the expression complicates a little bit more. So if you want to rotate the main axis of the transducer by an amount of theta naught degrees, then the expression is not anymore that lambda divided by d has to be larger or equal than n divided by n minus 1, but you get an additional factor of 1 plus absolute value of sine of theta naught, which basically means that, right, I mean, you can flip this and make this a minus, right? D divided by lambda would have to be less or equal than n minus 1 divided by n times 1 plus absolute value of sine theta naught. Let's say that you want to rotate the array, you know, to the maximum extent, which would be theta naught equals to 90 degrees, right? You want to make it equals going from minus to plus 90 degrees rotation. Then was 1 plus the absolute value of the maximum rotation angle would be a factor of 2. So now you need, you know, the separation of elements not to be roughly less than 1 wavelength, but you need it to be roughly less than half a wavelength. So if you want to rotate the axis, the aliasing effects are even more prevalent, and you have to have your elements even closer apart. FYI, typically, you know, when one builds ultrasonic transducers, for example, linear arrays, like the ones that you would see in clinical practice, typically the element spacing is about, you know, lambda, roughly a wavelength. And, you know, in some cases goes down to lambda over 2, basically to satisfy this requirement over here, just so you know. Questions? You've probably seen this already in the material, right? But this would be an example of that. If we have these to be the firing times, right? I mean, we're going to fire first this element over here, right? So this we fire first, then this, and then this guy, we fire it last, right? It kind of makes sense that this is going to tilt like this, because the ultrasound wave that this guy is generating, right, is going to take time to travel. And let's say that it will travel, oops, okay. It will travel up to, go back. It will travel up to this point, for example. And then the last element is going to travel, and travel. I don't know, up to this point. Actually, it will have to be up to this point, right? And it traveled a lesser distance because we fired it last, right? So the point where those waves are going to recombine is not going to be or contribute together, you know, but it's going to actually be here in this region. It's tilting towards the last element because that's the one that we fire last. And of course, you know, we fired every element in a sequence, of course, right? So that's why it tilts to the right. If we fire everybody at once, you know, again, you know, this will fire, and this guy will kind of do the same. And because both of them are fired at the same time, propagate in the same medium, right? Everybody contributes going to the front. And if we do the converse, right, we fire the first element last and the last element first, then we're going to tilt the beam towards the location of the first element in the array. And that's how it goes. Okay, that's more of a graphical representation, but it's basically stating the same thing that we were discussing so far. Questions?
It's clear.
Yes, sorry, I heard something and then nothing.
Yeah, I think it was Reno.
Oh, okay.
It was clear for me. Yeah.
Okay, awesome. Do you have a question, Peter?
Yes, about the, like, to rotate the axis of the ultrasound dot arrays is like equivalent to move all the arrays, the linear array, like as an all, around the axis to do this delay, right? It's exactly like the same.
I'm sorry, I think I didn't. Can you repeat the question? I think I didn't follow.
Like the linear array, if we move it around the axis physically, like moving, is equivalent to do this kind of delays.
Moving around the axis equals doing this?
Yeah.
Oh, okay. So if we actually rotate the linear array like this, right?
Mm-hmm.
Like if we fire all the elements at the same time, right? Then this would be pointing broadside, right? And then I rotate this and it will go like this. right?
Yeah,
And I rotate this and I will do like that. And yeah, so what the axis rotation allows me to do is that I can simulate this without having to do this.
exactly.
Correct.
Okay, thank you.
Mhm. And absolutely right, correct? That's the same idea. I mean, I cannot, like if I want to have the beam going that way, exactly, I will have to rotate this like this, and I can't, right? But what I can do is, you know, well, I can do it with electronic firings. I'm going to simulate that this is tilting like this, because I'm going to fire this guy first. So it's going to look like, you know, it's over here. And I'm going to do this one last. So it looks like it's over here. And it's even more intuitive when we look at the axis translation with ultrasound arrays. When we have a linear array, and this doesn't require any type of sophisticated anything, right? Let's say that we have this array with all those elements, and I'm going to turn on just the 5 that are shown in blue or green or turquoise or whatever that color is, right? And then I turn the next ones, right? I turn on not, you know, through to 6, but I turn on, you know, something like in this case 4, you know, to 8, right? And what happens is that the axis moved. You know, now the axis is still pointing, you know, in the front direction because I'm firing all the elements at the same time, but I moved 2 elements to the right. And then I repeat the same thing, you know, by shifting this, like 2 more elements to the right, and the beam of the transducer moved farther away to the right. And again, this, I mean, this is really not fancy at all, right? The only thing that I'm doing is I'm changing the ones I'm turning on. And with that, I have my beam marching left to right, and right to left, and left to right, right? So what is that simulating? Just like Birol said, right? I mean, if I were to like rotate this like this, like the other thing that I could do is I could move this left to right, right? Which I probably want to do, right? I mean, that's intuitively speaking, I want to do that. Because I have a transducer, and with the transducer I have one beam. If I want to create an image, right, like in a Cartesian grid, I will have to move the beam left to right. And if I were to have a single element transducer, the only alternative that I would have is to literally move the transducer left to right, correct? But with arrays, what I can do is I just decide which elements I'm going to fire, and I fire them sequentially, and I can move left to right. And again, I can also rotate, you know, left to right. And I can translate and rotate if I want to.
Teacher, and by translating, sorry, by translating the axis, by firing like a set of points at a time, would that impact on having less magnitude of pressure in the far field in the end?
Well, so in practice, right, in practice, if you have an array with, let's say, 200 elements, right, if you actually want to move your beam, you know, left to right, of course you will have to use less than 200 elements to transmit. Because if you do, I mean, if you use all of them, then there is no, I mean, there's nothing you can do, right? You just turn them on, that's it. So this whole thing is predicating on the assumption that you're only, you know, using a limited number of elements in your array to create the images, so you have that wiggling space, you know, to move left and right. By transmitting with a fewer number of elements, indeed, you are going to reduce the pressure, the amplitude of the ultrasound pressure that you're transmitting. That gets to be true. Regardless, you know, clinical arrays have the ability to transmit sufficient power, you know, up to the limitation points by the FDA on how much acoustic pressure you can radiate from a transducer. Yes, Jose, go for it.
Yes, I have a doubt when seeing this morphing. All the arrays are turn it off and then turning on, or just the ones that are changing to get that translation?
The ones in, I think it's turquoise. I'm going to go with that. The ones in turquoise are turned on, the ones in orange are turned off.
Yes. So for example, when I move to the right, I just turn one orange on and turn off one of the turquoise, or turn off
No,
all
I
the
mean,
turquoise and
remember
then
that
turn
when
on?
you're transmitting, you're only turning on the elements when you fire them, right?
Yes. Oh, okay.
Like, I guess my point is, it's not like you turn on a channel that stays on. You send a
Oh,
pulse through the channel, right?
Yes.
To each one of these guys, right? It's not like it's going to be like, you know, on or something. What it means is that at some point you're going to just transmit, you're going to feed them a sinusoidal signal probably, or a square signal, you know, some sort of oscillation that's going to make that element radiate a short pulse, and it goes away.
Oh, okay. I understand. Thank you.
That's the reason why when we were saying let's rotate the axis, right? What we said is we're going to introduce delays. Like if these were to be signals that are infinitely, you know, turned on or something like that, then that probably wouldn't make any sense whatsoever because it's always on, right? So, I mean, there is no concept of I'm going to turn on something. So yeah, I mean, this is basically saying that you're going to send pulses, but the time at which you fire the elements, you know, at which you send the pulse that's going to excite each one of the elements is going to be different when you rotate, right? And in this case, it's going to be the same time, right? All of them are at the same time. It's just that you decide which ones are going to transmit and which ones are not.
Oh, okay, and that have something to related with the time of flight of the signals, or not?
I mean, time of flight is basically just telling you that, well, it's just basically that, right? I mean, that if you have some radiator on, the time that it takes, you know, for the transducer, or sorry, for the ultrasound to make it from here to here, if this is a distance r, is going to be, you know, like the time is going to be equal to the distance divided by the sound speed, right? That's the time of flight relationship. Within the context of echographic imaging, just means that you have a round trip travel time. So there's a factor of 2, right? It's 2r divided by c, because it goes from the transducer to the reflector and then from the reflector to the transducer, right? But that's the concept of time of flight. Mm-hmm.
Thank you.
Sure, no problem. It is 4:10. So let's take, you know, a 5-minute break or something like that, so we can wrap up, you know, this whole description of ultrasound instrumentation, and we can have our second quiz of the course. Okay, so take 5, guys. Let's reconvene in a few minutes. And we are back. Let me see. Okay. Oh, and I have. Oh, okay. So Breno sent me a message. Let's try to talk maybe after lecture at some point about the office hours. So I seem to understand from what I read that there is no time of consensus for the office hours, right?
Yeah.
That's unfortunate. I
I
mean,
know.
it's just so troublesome that, you know, it would be so tough, you know, to find time. Okay, let's figure it out. So about the types of arrays that we can have, right? There are mainly 3 types of arrays in, you know, that are probably important to discuss for the context of these lectures. One of them is a phased array. Phased arrays, I mean, and these are pictures over here, you know, of arrays that we have in the laboratory at PUCP. Phased arrays are linear arrays, but they're like very small. By very small is, you know, the footprint, which like this would be the footprint. Okay. The overall length of the array. Actually, that's overdoing it, right? Because it's very unlikely that the actual array goes exactly all the way, you know, to the edge of the case of the transducer, but you kind of get the point, right? So that footprint is roughly 1.5 centimeters. And these are very small arrays, again, that are typically used in intercostal spaces, because this is typically used for cardiac imaging. Okay. The mechanism for image generation is beam rotation. And that sort of explains, you know, the way that cardiac ultrasound images would look like if you want to, let's say, go to the internet and look at one, right? Or, you know, afterwards, look at some. Sorry?
It's like a circular sector.
Correct. Mm-hmm. It's like a circular sector because of that, right? I mean, it's sweeping by steering the beam, right? Which is another way of creating an image, right? I have a small array in here, and rather than move left to right, what I do is this, right? Beam here, beam here, beam here, beam here, beam here, and I construct an image in polar coordinates, right? And that's why it has just a few elements, right? I mean, it doesn't have to have a lot of them because it's not scanning sequentially, you know, left to right. It just has a few, all of them are used all the time, and just keep rotating and sweeping. Because this is meant for cardiac imaging, right? You have to have some penetration anyway, right? You have to go several centimeters deep into the thoracic cavity. And you actually will probably get to read what these codes of the transducers are. And typically transducers will have some letters, right? And then a couple of numbers. And in this case, the numbers are 4 and 2. That means that the transducer has a usable bandwidth in between 2 and 4 megahertz. Why not 2.4 rather than 4.2? I don't know. I mean, I'm not that old that I would be able to tell you, you know, how is it that people started labeling these things. Old enough to tell you that's how it is, right? So again, whenever you have arrays that operate with some sort of a polar scanning, right, or a sector scanning rather than a Cartesian scanning, it typically will operate at low frequencies, because those type of, you know, polar scans are usually when you want to have a very large field of view. And, you know, laterally you have it by rotating the axis or whatever mechanism for the polar scanning, and axially you have it by, you know, operating at low frequencies so you can propagate to infinity and beyond without worrying about attenuation effects. The other type would be a linear array, right? Like this one over here, which is an L for linear, right? And then 14.5. So you already know that that basically means that, you know, the bandwidth goes from 5 to 14 megahertz. These arrays use translation, beam translation, as a mechanism for constructing the image. That being said, you know, you can, you know, shift your beam left to right, left to right, left to right. And then when you're over here, you can steer a little bit so that you can have like a trapezoidal view, and that's like a panoramic view. It even has a name, right? That's kind of funny. The active surface is longer than for the phased arrays, of course, because this is moving the beam left to right. So rather than being a small 1.5 centimeter aperture, you have a relatively long, let's say roughly 4 centimeter aperture for most of the linear arrays. You don't make them so big that, you know, it becomes impractical. You cannot, you know, place it anywhere, but you make it big enough that, you know, you can move your beam left to right. Typically, it has several elements. 128 would be like a low end. It can go up to 256. Typically, you know, but that's the range of, you know, number of elements I will have. Frequency wise, again, it goes to high frequencies because, right? I mean, even though the surface of the array is longer, or the length of the array is larger, it's still a relatively limited field of view. So linear arrays are used, for applications where you're going to do very superficial imaging. So you care about very high resolution, you care about, the highest frequencies that you can get, but you're only limited, or you're only wanting to look at things that happen in a relatively small field, in front of the transducer with a relatively limited depth. So you use it for breast imaging, use it for thyroid imaging, use it for MSK, you use it for superficial imaging, skin imaging, for example, but that's usually how it goes. The third type of array that you will very commonly find equipped in scanners in clinics and hospitals are curvilinear arrays or curved arrays. So again, you have the codes, right? It's C for curved, and then 7.3, which means it's spanning between 3 and 7 megahertz. This one also uses beam translation as a mechanism for the beamforming, okay? But the issue in here is that the surface of the transducer is curved. So when you're firing the elements, right? I mean, of course, in here it will go from, but then, your array locally is tilted, right? So propagating a beam to the front makes the beam go this way, and then it will be this way. So what you end up having is also, some sort of a polar scan. And there's a reason why when you create images with this type of arrays, I mean, it's also diverged in a way, it's also in polar coordinates, right? But again, it operates under the principle of shifting your aperture rather than rotating it. Typically, the active surface is large because this is used for things like abdominal imaging, for example. So you want to look at a very big field of view. Your active surface can be like 5 to 6 centimeters. And because this is translating the axis, you have a relatively large number of elements too, which is typically about 128. You can effectively, shift your aperture left to right. Questions up to this point?
Teacher, so focusing is not actually used in clinical settings?
Yes, it is, but we have not gotten there yet.
Oh, okay.
That's kind of the thing, right? One of the main drawbacks when we talked about, focusing a circular piston was you had to have the transducer curved, right? And of course, you can imagine you can manufacture, that transducer in the shape of, a spherical shell. But if you want to focus at a different depth, then it will have to have a different radius of curvature. And if you wanted to have a different radius of curvature, then you have to, make a different transducer from scratch. You cannot just deform it on the fly, right? And that gets to be impractical. Because if you want to create an image and you want to be focused at, 2 or 3 different locations, you will have to first scan with the transducer of the first focus and throw it out, and then the other one, and throw it out, and then the other one. And by the way, that would imply actually moving the transducer, which in itself is a challenge, right? So it was not feasible, it was not practical. With arrays, everything you can do, you just do it by applying different delays to the elements. So instead of actually physically focusing the transducer by, curving it, you electronically focus the transducer by applying different time delays to each one of the elements. So you can actually have the same transducer and you can focus it at, arbitrary depths, right? I mean, it's the same transducer, you just change the delays that you send to each one of the elements, and you can actually focus it on different depths. And the idea is relatively simple, right? When you really think about it. What did we need in order to focus an ultrasonic beam. What we said that we needed was we grab the transducer and we curve it so that every point in the transducer is at the same distance away from one location that we call a focal point, right? Okay, so we cannot again curve the array, right? I mean, we're not going to grab the elements and move them physically. But what I can do is I can fire them at different, firing times such that the waveforms that each element transmits arrive at the same time to a focal distance, right? So basically it would be something like this, right? I mean, I have ds, I have the e to the minus jkr, and then I apply my delay, which is a minus j omega tau sub I to the f. I mean, I just apply some focusing, right? Some tau. Where r sub I, right? We already know that that would be the distance, right? From the from one element in the array to the focal depth, right? So as a square root of c squared plus I prime d to the square, right? Where I prime is, it's just the location, right? So I times d is the location of the element in the array, and then z is the depth, right? So when you really think about it, right? And if you look at these expressions, how can I make this become as if everything is arriving at the same time? The only thing that I need to do is to match these two terms over here. Like I apply delays, right? And at this point, I'm not using any type of far field approximation whatsoever, right? I mean, this is just the original equation. And the only thing that I need is that the arguments of those two exponentials cancel each other, which means, technically speaking, right, that I need to apply delays that are equal to minus the distance from the elements to the depth that I want to focus at divided by the sound speed. Which, when you really think about it, it's very intuitive, right? I mean, I probably don't even need that equation to tell me that's what I need to do. What basically saying is, if you want all the signals to arrive at the same time, you have to fire at different times, and those times have to be proportional to the distances in between, the focal depth that you want to have and the positions of the elements in the array. So when you want to focus, right, you can focus on transmit and you can focus on receive. And this is one aspect of focusing that sometimes confuses, students. The first time that they think about it. If you were to have a circular piston, right, just a solid piston, it already has a beam, right? So if you transmit, there will be a beam. And when you receive, there will be a beam, and both of them will be the same, right? And they're the same because, I mean, the transducer already has a shape, right? So nothing changes. And when I send electricity through it, it will generate, some pressure beam, and something will happen. And when it's in the presence of a pressure beam, right, somewhere, a pressure signal, it will generate some, some measurements, some electrical measurements, and that's going to also be due to the beam of the transducer. It just has one beam. But remember that with an array, technically speaking, what I have is a whole bunch of elements, right, that I electronically excite in different fashions, right? I turn some on, some others are left off. I apply delays, right? And the delays can be, those, the delays can be proportional to the distance, so I can, focus the beam, or they can be sequentially increasing in a linear fashion. And with that, I would be steering the beam, right? Or I can do any sorts of crazy stuff, right? I can fire them at will as I want. And that would be on transmission, right? But when you really think of how this would operate on reception, right? On reception, there is something that's generated in a medium, and there's a pressure waveform that hits the array, right? and I'm going to record an electronic signal for each one of the individual elements. The main difference, and this is a significantly profound difference, is that when I transmit, in order to focus, right, I need to fire elements, I need to decide at which time I fire each one of the elements, and physics will take care of, the beam happening. When I do it on receive, the signals make all the way to the elements of the transducer, right? And what I need to do is I need to do the same thing. I need to apply delays. But the delays, I apply them electronically. It's like delaying signals that you have recorded on a computer, right? And that I just basically do, operating with, my computer. I shift the signals and I combine them together. So beamforming on reception, I can do arbitrarily. I can actually, with the same signals that I receive, I can, for example, focus at an arbitrary infinite number of focal depths. But in transmit, it's not the case. In transmit, if I want to focus at 2 depths, I need to make 2 transmissions. If I want to focus at 3 depths, I need to make 3 transmissions. On reception, I just receive the data, and if I want to focus on 100 depths, I just, shift and combine the signals 100 times. This is the same signals. So beamforming on transmission, limits me on how fast I can create the image, for example, because it's something that, bores in the electric signals and then physics happen. On reception is the other way around. Physics already happened. That's the part that limits me in the time frame, that I can have for, obtain more measurements from the ultrasonic system. After that, shifting and adding, that's done electronically. And this is basically the concept, right? I mean, if you were to have an array, right, like this, and then there is one element in here, right? I mean, and this element, sorry, not an element, a reflector, and the reflector is generating a wavefront, right? So I'm going to have a signal that's going to take longer to make it to the elements that are, towards the edges, and then it's going to take a shortest time to make it to the one at the center, which is this. I will get a reflection, or I will get, a waveform that is closer to time equal to 0 for the element that's right in front of the reflector. And then as I start to go to the sides, right? I mean, it's the echoes occur later and later and later in time. If I apply focusing, right? That means that I apply delays, just like we said before, delays that are minus R sub I divided by C. So this goes to the left, right? So if the reflector is actually at the depth that I think it is, after I apply all those delays to the signals, all those sinusoidal echoes would be aligned one on top of the other. If I sum them, I will get a very large oscillation, right? But if the reflector was not at the depth that I thought it was, right, and I apply delays, they would be the wrong delays. So my signals are not landing on top of each other. And when I combine them, you get a weaker signal. So that's how beamforming on reception works. You delay the signals and you sum them. That's the reason why the algorithm is literally called delay and sum. Because that's what you do. You delay and you sum. You delay and you sum. You do that for every, so you have your transmission and you have your receiving apertures. You do that for each one of your receiving apertures, right? For the depth that you want to focus at. And if you want to focus at the second depth, you calculate a new set of delays. You delay again, you sum, and so on and so forth. Okay? So that's how it goes. Questions?
So if I'm not understanding, but you do the same thing, but the only different thing to focus is done in the computer.
Correct.
But after that, we do the same. Like we fired each each of the elements at the same time?
You fire each one of the elements at the same time. No, I mean, it's not that you fire all the elements at the same time, right? I mean, you fire them however you want to fire them, right? I mean,
Okay.
typically you fire them, you know, with delay so that you're going to be focusing the beam at some depth.
All right.
Right?
Then
And then you
that,
start, you know, getting echoes.
yeah.
The thing is on receive, right? So when you start getting the echoes, that's the part that typically confuses people, because in transmit, it's like, okay, fine, I understand this. Okay, it's fine. So on receive, it operates under the same assumption. It's just that it's a reciprocal, right? How do you do it on transmit? On transmit, you need to generate a pressure waveform. So what you do is you excite at different moments, right?
Yes.
It's like a delay, but because you're firing them, right? Each one of the contributions of the individual elements combine to create a beam. That combination is not something that you do, right? It's something that the real world does.
Yeah.
You just fire the elements and then the pressures are going to combine. They're going to sum with one another, right? That's basically what we are assuming it happens, right? The contribution of each one of the elements gets summed together and it creates an overall pressure field. Going the inverse way, right? The pressure field already exists. So you have some vibrations that are trying to hit the transducer. They hit the transducer and they generate electrical signals. So you have to do the same thing that you did in transmit, which is you need to delay them in a way that you focus, for example, or that you steer the beam, or you do whatever you want to do, right?
Yeah.
And you also have to sum them, right? Just like you didn't sum them, but you let physics and God, combine the transmitted waveforms and create an overall field when you transmit it. You have to delay the electrical signals and then you need to sum them. But this you do electronically.
Right. After we record them.
Correct.
Okay.
That's the thing, right? Because you already have the signals stored in memory, right? Because the really silly way of doing it would be you apply some delayed lines, right? So the delays are fixed, and then you short circuit your signals, so you connect your signals so that everything would electronically add. But that wouldn't make any sense whatsoever, because you can do it on your computer, and you can do that without any hardware, just doing it based on software.
Yes.
And that again is the fundamental difference of what happens. Like the way that the shifting and adding happens in transmit is physics driven. The way that the shifting and adding works on reception is computer based.
Yeah. Okay, I understood it.
Awesome. And don't get me wrong, it's a tough concept to grasp the first time that one gets to hear about it. Okay, so don't feel bad if you have questions about it. I also uploaded some material for you to review on just some examples of beam mode images. We're not going to necessarily cover it in discussion, just some applications, so you get to see things like, for example, ultrasound is well known for obstetrical imaging, for thyroid imaging, for gallbladder imaging, there's breast imaging. There are so many different applications, so you can roughly get an overview, of what ultrasound could be used for. But, technically speaking, clinical applications, there are plenty, right? I mean, the idea was not to give a lecture on the radiology of the medical imaging, but you get to, tie the link with some of those images to the engineering concepts that we have been describing. Now, your quiz should be active. So please get started. Remember, you have 20 minutes overall, so it's like 15, 16 minutes to get over with the quiz, and then you have 4 minutes to upload your solutions. You have 20 minutes, make them work, okay? Go for it. If you have any questions, please let me know.